When forces balance, an object is still. This is called force equilibrium. This is statics, where sigma F equals 0. The problem is an object in equilibrium can still stretch. Then what is added here is solid mechanics. Solid mechanics is statics, but among statics it looks in detail at how stress behaves. Does it stretch or not? There are cases where F is not 0, right? That means it's MA. This is called dynamics. Dynamics is a course that students learn in their second year, so if you properly learn general physics, the rest becomes incredibly easy. It's all connected. This is why you'll realize that F equals MA is important. You'll be studying Newtonian mechanics throughout your degree. You'll learn about F or MA. I think it would be good to know, instead of memorizing, just knowing that such forces exist, or when you draw a free body diagram, if you frequently use these forces, you'll naturally adapt more easily. Got it? Now just remember it as tension T, just memorize it like this. Then this is Kx. Then the vertical force is called normal force, N. This way, N. The supporting force. Then gravity is one of the invisible forces pulling down towards the center of the Earth. Next, frictional force is opposite to the direction of motion. If the motion is this way, the frictional force is that way. You just need to know it like this. Now let's talk about why we learn mechanics. Let's start with the word itself. In physics, mechanics is simply the study of forces and their effect on objects, the study of force. Take a look. Why do we need to learn about force? The reason is simple. Ask people around you, why do you learn mechanics? Why do we need to learn mechanics? Not many people can answer if you ask this, but let me tell you. The reason for learning mechanics is simple. We are interested in objects, not people, right? We are interested in objects, right? But an object is only interested in one thing, force. It's only interested in force and nothing else. This is a bit out of the blue. Let me give you a simple example. This object is like this, right? If this object, let's say an object called M, is on the ground, this object really isn't interested in anything else. For instance, if an attractive woman walks by, people will instinctively turn their heads to look. Men do, right? And women might react with a sharp, competitive glare. She might glare thinking, she's prettier than me. And a man might look because he thinks she's pretty. But an object doesn't move. It doesn't even tremble. And it is not interested in women. And it is not interested in money either. Money. If you put money here, if you put 1,001 or 10,001 next to it, does the object react? It doesn't react. It doesn't react because it's not interested. But even if you put 50,001 there, it doesn't move. It doesn't move, right? But what about people? The money might disappear later. Money doesn't have legs, but it can disappear from that spot. So people do react. They react to various things. This object, however, does not react even to political power. Objects are only interested in force. You apply force like this, F. Then it reacts. An output comes out, reaction. Only when you apply force does an output come out. No matter what you place in front of it, it doesn't react. That's why psychology is difficult for people. So what is psychology? It's about studying people. Psychology. Students from the engineering college or the natural sciences college will take this class, and they should really be thankful. Psychology is so difficult because you can't know a person's mind. A person's mind is different case by case. Psychology is incredibly difficult, right? But mechanics? It's so much easier because you only need to learn about one thing, force, just force. It all comes down to this. Objects are only interested in force. That's the entire reason we study mechanics. Objects only react by moving, shifting, or accelerating in response to a force. And that's why we learn this field. Makes sense. Okay, so we learn mechanics. Got it. You wanted to learn mechanics. And I understand that mechanics is about how objects react, so you guys draw graphs, right? Okay, got it. Then you will learn about free body diagrams. Now this is important. The reason it's important is that students need to know how to draw free body diagrams. Now let me tell you about the case for engineering students. Engineering students start learning mechanics in their second year. The free body diagrams they learned in their first year will be used until they graduate in their fourth year. They will use them a lot in their second year, a lot in their third year, and a little less in their fourth year because mechanics is almost finished by then. So you draw free body diagrams for 4 years. Then why do you draw free body diagrams? You need to know this too, right? The reason for drawing free body diagrams. It's because a free body diagram is all about showing you the result. It's about getting to that final conclusion. The reason it's so important is because it tells you exactly what that result is. Let me give you a small example. Suppose there is a director. Let's say this is the CEO. Then someone will come and report, right? An employee has come to make a report. A report. Then what is what? They will talk about how much sales product A made and how much sales product B made, right? Then what does the CEO say while listening? Is it a profit or a loss? That's what they ask. Is this year's sales a profit or a loss? That's what they're asking, the result of the report. The reason this person discusses sales is that companies are primarily interested in making money, so they examine financial statements and similar documents. That's why they talk about results related to money, using these financial statements to listen to the report and hear the conclusion. Do you understand? It's the same. It's the same principle. An object is only interested in forces, so a free body diagram is a tool for seeing the net result of those forces. That's why you draw the free body diagram. Let's try drawing a free body diagram for this object. In the next lecture, or the one after that, I'll teach you how to draw a free body diagram in detail. For now, just take a look. So when you draw a free body diagram for this object, I'll explain why it's called a free body diagram. This object is called a free body diagram, right? It's talking about just leave this object alone, just the object. Then, what about things other than the object? You ask, right? Then things other than the object can be changed into forces. Do you understand? You can change everything outside the object into forces. You know, this reminds me of a classic scene you see in movies all the time. Some employees give a long, detailed presentation to a tough CEO, and the CEO just cuts right to the chase and asks, "Okay, but will it make us money?" For that CEO, the only thing that's truly important is whether or not it makes money. He doesn't care what the product is or what it's about. The only thing that matters is the final profit. It's the exact same idea here. There's no need to draw anything other than forces in this free body diagram. Does it become a force? That's the point. If you leave money here and then give 50,001 here, it doesn't matter when drawing the free body diagram. Because this money is meaningless, and what is it? It doesn't become a force. This 50,001 cannot be converted into a force for it. So, in a free body diagram, no matter what picture is next to it, you just leave the object like this. And for the rest, leave it as is and change the rest to force. This is a free body diagram. So, you let the object float freely by itself, and the rest? You represent it with forces. We do this because a free body diagram is like an object's financial statement. It allows you to show only the forces that the object is interested in. That's why we draw them. All right, let's begin. First, tension. That's T in this direction. Like this. Then there's elastic force, right? Then Kx in this direction. If you pull like this, it will pull in the opposite direction. Then what else is there? What's acting downward? Even though it's not visible, there's gravity, mg, right? Then what about the surface? The surface exerts an upward pushing normal force, like this, N. Okay? Then it can be represented like this. Cutting off the rest and converting them all into forces is what a free body diagram is. Got it? So the conclusion is, why do we do this? This is the most important part. This is all to explain why the equation F equals ma is the most important one. Look, in the end, how is it moving? It says here that it is accelerating in this direction. So if you combine this and this, it becomes 0. 0, so we use the Greek letter sigma. We'll analyze the sum of forces in the x direction, sigma fx, and the y direction, sigma fy. Once you find this, it's done. Sigma fx. What is sigma? Sigma represents the sum, so it means to add up from x1 to n. Then what forces act on the x-axis? There's only this one, right? So you can put it in as kx minus t or something like that, and what about here? There are only forces on this side and that side, right? This becomes n minus mg. Do you understand? So let's sum the forces. In the x direction, we have acceleration, so the sum of forces equals ma. But in the y direction, what's the sum? It's 0. It doesn't go up here or sink into the ground, so the acceleration you find will be negative, right? Because the acceleration goes to the left. So like this, force is mass times acceleration. Then what happens if you know the acceleration? If you know the acceleration, then it's done. This is called the net force. Things like this. This is the net force on the x-axis and the net force on the y-axis. So this is the bottom line question, like asking profit or loss. In physics, this translates to, is there a net force, and does it cause the object to accelerate? You understand, right? So that F can equal ma. Do you understand? The reason for finding the net force is like determining whether it's a surplus or deficit, whether there is acceleration or not. If you add it all up and it represents that, then what happens? You can find A, right? M will be given, won't it? Like 10 kilograms or something, right? So if you sum up all the forces, you'll get some value in newtons, right? For example, let's say it comes out to 100 newtons. If the mass is 10 kilograms, what does A become? A becomes 10. It's negative 10. So if the acceleration is negative 10, what happens next? Are you all starting to see the connection now? What can we do when we get A? We can draw a graph, right? A graph. You can draw a graph like minus 10. If we assume there is no initial speed, it makes sense. You can draw an acceleration time graph, a velocity time graph, and a displacement time graph like this. You can understand all the states of motion. The conclusion is, by drawing a free body diagram, what you will find out is, now I will write the key point here. Conclusion. Students like conclusions, right? The conclusion is that we find A through the free body diagram. A. Do you understand? Because force is mass times acceleration, right? Mass will be given in the problem anyway. Then, if you find the sum of the free body diagram, acceleration comes out because of the mass. In conclusion, acceleration. What happens when A comes out? Then draw the graph. In dynamics, this is the entire process, and it's the same for statics and solid mechanics. To draw the graph, we find A, and to find A, we can use the formula F equals ma, but if various forces are acting, we find A using the net force equation. We'll be doing this process together from now on, constantly. So everything up to now has just been a warm-up. You've been drawing graphs and studying one-dimensional and two-dimensional motion, right? Through graph drawing, students have now learned about various types of motion, such as parabolic motion, circular motion, and one-dimensional motion. But they didn't know how the acceleration was given. Until now, we just drew graphs by saying the acceleration is 10 or gravity is acting. But from now on, after teaching the force, we have to find the acceleration. Once we find the acceleration, we can immediately draw the graph, and the object can react by moving with constant velocity, with constant acceleration, or it might not move at all. The output reaction like that. You will now learn how objects react in this mechanics. Got it? If this content is too confusing, not knowing this part won't affect solving problems, but understanding this concept will make it easier for students to learn mechanics. You will understand why we learn mechanics. It's fun. Physics is fun too. So the important thing here is that we need to remember the formula F equals ma. This is Newton's law. This is Newton's second law. Then Newton's second law is through the free body diagram, because the free body diagram only cares about forces acting on the object, as it represents all the forces. So what do we find using the FBD? We find sigma F, the net force. From the net force and F equals ma, we can find A. And once we have A, what can we do? We can draw our graphs. It could be one-dimensional motion or two-dimensional motion. What is this? This is the output. This is a reaction. The object is responding to the force. It shows a reaction. So this is called mechanics. This is Newtonian mechanics. Newtonian mechanics. The reason it's called Newtonian mechanics is because Newton proposed the formula F equals ma. So instead of calling the unit of force kilogram meter per second squared, he used his name, Newton, to denote it as N. Now, if there's a problem like this, I'll briefly introduce it and then finish. Now, in Newtonian mechanics, there is a possibility that the sum of forces, sigma F, could be zero, right? Zero, correct? When you add them all up, it could be at rest, right? Correct? This is called equilibrium of forces. Equilibrium. This equilibrium problem will come up soon, but this is just statics. This later develops into statics. But in statics, there's only one rule. Sigma F equals 0, and that's its limitation. The problem is, even with force equilibrium, an object can still stretch, like a spring. Then what is added here is solid mechanics. Do you understand? Solid mechanics is statics, but within statics, it looks more closely at how the stress behaves, whether it increases or not. Then there are cases where sigma F is not a 0. So it's ma, right? Ma. A is not 0. This is called dynamics. Dynamics. This is about movement, right? So, mechanics of motion. The resulting net force is what causes the object to move. Students learn this through a subject called dynamics in their second year. So if you learn general physics properly, the rest is really easy. It's all connected. This is why you'll realize that F equals ma is important. You'll be studying Newtonian mechanics throughout your degree. You'll learn F equals ma. Therefore, if students study while understanding this concept, it will be helpful. Got it? Next time, we will apply this and cover in detail how to draw free body diagrams, so make sure to focus, work hard, and review thoroughly. Good job.